So in today's lesson, we're going to be working through a concept that is pretty central to chemistry, and so well worth you investing some time to make sense of it. And that concept is the mole. And so the mole is an actual measurement. So we're not talking about the organism, the mole. We're not talking about a skin tag on your face. We're talking about a measurement. And so I'm going to go through that today and help you to familiarize yourself with it. So in order to scaffold this properly, I'm going to start with a concept that you're really familiar with and then extend it to this new concept, the mole. And in so doing, I'm going to also remind you of some basics of dimensional analysis that we went through in earlier parts of the year. Let's start off. So I've got some questions here that will probably seem pretty simple, but I also want to set it up and remind you about what we do to analyze units. So in this first question, I'm saying, how many donuts do you have if you buy one dozen? And so I know that by definition, this is the unit conversion factor, if you will. I know that 1 dozen is equal to 12 of anything, right? 12 pieces, right? And in this case, the pieces happen to be donuts, right? So I know that if I have 1 dozen donuts, and I know that there are 12 donuts for every 1 dozen, then I've canceled out donuts, dozens of donuts, and I've got 12. And so of course we know that there's 12 donuts in a dozen. That's a no-brainer. But there's our setup. So now let's apply that to a different problem. So because I can have a dozen of different things, right? So in this case, I have 24 eggs. And so I think, in your mind, you already know, well, if I have 24 eggs and each dozen is 12 eggs, then I know that I have 2 dozen. But let's set that up as a mathematical analysis. So I know if I have 24 eggs, right, and I don't want eggs, so I'm going to get rid of the eggs down here. All right, and I know that there are 12 eggs in 1 dozen eggs. All right, so my 24 divided by 12 is going to give me my 2 dozen. And so, you can see how in more complicated questions that analyze it in this way might make it easier to solve, and we're certainly going to have to do that in the next steps. So let's look at this. So if you were to purchase 3.5 dozen donuts, how many donuts would you have? All right, so I know that, if I have 3.5 dozen of anything, that I know that I have, in 1 dozen, I always have 12 pieces, right? In this case, the pieces just happen to be donuts. Right? And so that will allow me to figure out exactly how many donuts that I have. So 3.5 times 12 gives me 42. Now we could have worked that out, but again, because the numbers are kind of quasi-friendly here, we can just sort of mentally work that out. And I don't want us to forget that as we're working through the next problem, but it does give us a bit of a system to break this down. All right, so now in the same way that a dozen, we know dozen means 12 pieces. In chemistry, we have this sort of collective term that when we use it signifies a very specific number. So just as 1 dozen can mean 12 of something, and usually we're talking about donuts or eggs, but we really could apply it to anything. In chemistry, 1 mole means 6.02 times 10 to the power 23 of something. Now, usually we're talking about atoms or molecules, chemical particles of some type. So let's, so for instance, I could have a mole of donuts, but that would mean I would have a whole heck of a lot of donuts. In fact, let's break that number in scientific notation and write it in standard form, right? That would be 602. Now I need to add 21 zeros. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That's a lot of donuts. In fact, I think if you were to cover the surface of the earth with donuts, you'd need it to be like a kilometer thick or so to make it have a mole of donuts. So pretty large number. And so you might be asking, well, why the heck are we using the mole? Why not just use like, atoms or molecules? And so I do want to talk about that. And I'm going to get there in a minute. So just to be clear, I want you to know that when I say 1 mole, I'm talking about this value specifically, the 6.02 times 10 to the 23 atoms or molecules or particles of any kind, right? But that is referred to as Avogadro's number most famously. So if we say use Avogadro's number, we're talking about this value. And that's now named after Italian scientist named Amedeo Avogadro, who was involved in studying gases, and eventually to honor him had his name associated with this value in chemistry. All right, so now why the heck are we using this? Well, because when you take a small amount of matter, and I'm talking like small, so for instance, a tiny drop of water, right, which is about, I don't know, like half a milliliter, not very much, right? A small amount of matter is going to contain a whole whackload of molecules, okay, or particles, whatever the species might be. So, for instance, if you were to look at 1 drop of water, that has about 1.5 sextillion water molecules in it. So small little piece of matter, huge number of molecules. So that makes working with those larger numbers is a lot more, it's a lot more difficult to work with. So we use the mole to just simplify the numbers, right? So 1 sextillion, just FYI, would be this value. So that's huge. So working with moles just allows the numbers to be a little bit easier to work with, so that, we're less prone to make mistakes with big, large values here. Okay, so let's take a look at some examples to get us started, just so that you know what the types of calculations you might have to do in relation to the mole. So here's the first example. So when I look at this question, I'm going to first analyze what information I have and then how I can utilize that. And I'm always going to think of that mole value as being almost like a unit conversion factor, that 1 mole is equal to 6.02 times 10 to the 23 pieces. I'm going to write out pieces. And so the pieces, depending on what the pieces are, that might change the calculation slightly. But we're going to think of that as a unit conversion factor. Okay, and so I'm going to start, first of all, it says I have 5.93 times 10 to the 24 atoms of silver is equivalent to how many moles? Okay, so we're going to start out with the simplest case here. And I'm going to say, well, if I have 5.93 times 10 to the power of 24 atoms of silver, and I don't want atoms of silver, so I'm going to get rid of those atoms of silver by putting them on the opposite side of the fraction. Okay, so atoms of silver. But I do want moles of silver, so I want moles of silver. And see, just by this alone, I can see that these atoms of silver will cancel and I'll be left with moles. So now I'm left to write out, well, what is the equivalence between those 2 units? Well, I know 1 mole of silver has exactly 6.02 times 10 to the power of 23 atoms. Okay, and so I'm going to multiply across and then divide out, and that's going to give me my value in moles. And so when I round, and I need to be careful about rounding here, right? So here I have a value with 3 significant digits, and so I'm going to round my value to 3 significant digits. It should be 9. Oops, let me change that to a pen. 9.85 moles of silver. Okay, and so there you can see that I've simply used this equivalence here in order to calculate my moles. Let's try another question. Okay, and so I'm going to encourage you to give this a go to see how you do, and then pause the video and resume when you're ready to take it up. Okay, so when I look at this question, I know that I am asked about 2.2 moles of water, and I want to know how many molecules. Okay, so because water comes in molecules, I'm just finding out really how many pieces of water I have here. And so I'm going to go ahead and say, well, I have 2.2 moles of water, but I don't want moles of water, so I need to cancel them out. So my moles of water, I'm going to go down here. And I know that there are, in 1 mole of water, I have exactly 6.02 times 10 to the power of 23 molecules, or pieces of water. Water comes in molecules, right? So that's what the pieces would be called. And so looking at my unit analysis here, I can see that moles of water are going to cancel, and I'm going to be left with molecules of water. So I'm simply going to go 2.2 times 6.02 times 10 to the power of 23, which is going to give me a value that I'm going to round to 2 significant digits. I'm getting 1.3244, but I'm going to round that to 1.3 times 10 to the power of 24, and that is molecules of H2O. All right, I am on to the next question. All right, so now I want to up the ante a little bit. I want to make this a little bit more involved of a question. So here we're saying, how many hydrogen atoms are there in 0.78 moles of ammonia? Okay, so I'm going to just remind you what the formula for ammonia is. Ammonia has the formula NH3, and that's comes up quite often, so it's probably a good one for you to know. And so notice that the question is not asking me how many molecules of ammonia, it's asking me how many hydrogen atoms would be in that many moles of ammonia. So I've got a couple of different things going on here. And so my strategy with this would be to say, well, if I have that many moles of ammonia, I can certainly figure out how many molecules of ammonia. And once I have molecules of ammonia, I can then figure out hydrogen atoms, because I know there are 3 hydrogen atoms for every whole ammonia. Let's do that. Let's break that down. And so I'm going to start with what I know, which is 0.78 moles of ammonia. But I don't want moles of ammonia. So my moles of ammonia are going to go down here. And I can't really go directly to hydrogen atoms from here because I don't know how many moles of hydrogen atoms I have. So I'm going to figure out how many molecules I see because of ammonia I have, because that's something I do know directly. And I know that 1 mole of ammonia is always going to have this 6.02 times 10 to the power of 23 pieces. And in this case, the pieces are molecules. Right? And so if I stopped there, let's do the unit analysis. I've gotten rid of my moles of ammonia, and I'm left with molecules of NH3. But again, I want to know hydrogen atoms. So I'm not quite done here. And so the next thing I need to do is say, well, I don't actually want molecules of ammonia. So I need to get rid of that. I'm going to divide those out. Molecules of ammonia, right? And what I want to get are hydrogen atoms. Well, I know that for every 1 ammonia molecule, I have exactly 3 hydrogen atoms. And so now I'm all set up. And so I've been able to eliminate my units of molecules, and I'm left with hydrogen atoms as the remaining unit. So multiplying and dividing across, I get 0.78 times 6.02 times 10 to the power of 23 times 3. And so my unit analysis is telling me that I need to use 2 significant digits in my response. So that's what I'm going to do. I have 1.4 times 10 to the power of 24 hydrogen atoms. So that was a bit of a step up. So hopefully you found that to be not too bad. Let's take a look at another example that's pretty similar. So in this example, it says how many oxygen atoms are in 0.35 moles of sodium nitrite? And so you can see here that there's a dependence on you knowing what sodium nitrite is. And so just to make life simpler on this video, I'm going to give you that formula, but it's well worth you investing some time and knowing your nomenclature, chemical naming, to help you out with these mole problems. So sodium nitrite would have the formula NaNO2. Okay, so pause the video, give this question a try, and then resume when you're ready to take it up. Okay, so in this question, they're saying how many oxygen atoms are in 0.35 moles of sodium nitrite? So the approach to this problem is going to be pretty similar to example number 3, our previous example, where you're first going to figure out how many moles of this particular compound you have, how many particles, I should say, and then that will translate to oxygen atoms at the end. Okay, so now sodium nitrite is an ionic compound, and so I don't like to call ionic compounds molecules. There's no covalent bonds, and so we can call those formula units, or we can call them particles. I like just particles. It's a nice general word to use, so let's go with that. So I have 0.35 moles of sodium nitrite. But I don't want moles of sodium nitrite, so I'm going to get rid of that by putting it in my denominator. And I want particles, or formula units, of NaNO2, right? And I know that in 1 mole of that substance, I'm going to have that Avogadro's number value, 0.02 times 10 to the power of 23, formula units or particles of sodium nitrite. So if I stopped there, then all I would have accomplished would be to get rid of moles of sodium nitrite and get the number of formula units of sodium nitrite. But I don't actually want that, so I need to keep going because the question's actually asking me how many oxygen atoms, right? So I'm going to say, all right, well, I know that I'm looking at particles of sodium nitrite, and I want oxygen atoms. So in positioning my particles in that way, I have canceled out that unit, and the unit that will remain will be O atoms. So the last thing I need to figure out here is, well, what's the relationship between particles and O atoms? Well, I know that for every 1 particle of NaNO2, there are 2 oxygen atoms. And so now all I need to do is multiply across, divide out, and end up with my answer. And so again, I'm looking at my significant digits. I've got 2 significant digits here, so I'm going to round my answer to 2 as well. 4.2 times 10 to the power of 23, and that is oxygen atoms. Okay, hopefully you fared okay for that example. Let's try one that's just a slightly bit different. So in this question, it says how many moles, so I'm going to be looking for moles of carbon dioxide could be made with that quantity of oxygen atoms. Okay, so I want you to envision that we would have a bunch of oxygen atoms all kind of there available to react, right? Of course, this is diatomic, so it would be O2s, but you know, the idea is the same. So how many oxygen atoms would we need to group together to make our CO2, right? So how many oxygen atoms would need to be available to make a certain number of moles of carbon dioxide, right? And so that's the question at hand. So if you're ready, you can pause the video and try this question out if you want to give it a go yourself. Otherwise, follow along with my explanation. So my strategy here is to start with what I have, which is 6.3 times 10 to the power of 22 oxygen atoms. Right? And so I eventually want moles of CO2, but I can't really go directly from oxygen atoms to moles of CO2. That's not going to be possible. So what I'm going to do is I'm going to say, well, I have like a bunch of O's that are like I'm going to think about as being sort of separate. And then what I'm going to do is I'm going to say, well, I know that for every 1 CO2, I have 2 oxygen. So it's almost like I'm just going to sort of group these together, and each of them is going to go to making 1 CO2, right? So bear with me here. So I need to, I don't want oxygen atoms. I'm going to say, well, how many CO2 molecules can I make, right? And so I know for every 1 CO2 molecule, I'm going to need 2 oxygen atoms, right? Because I'm grouping them every time I do that. Okay, but again, I don't want molecules of CO2. I want moles of CO2. So I need to keep going. So I'm going to say, let me just fit this in down here. Well, I want to get rid of CO2 molecules. I'm going to put those in my denominator. And I want moles of CO2. So that's a relationship that I'm familiar with, right? Because 1 mole of a certain type of piece is going to be equal to 6.02 times 10 to the power of 23 pieces of that substance. And so, I no longer have units of CO2 molecules, and I would have units of moles. So working that calculation out, I have 6.3 times 10 to the power of 23 times 1 divided by 2, and then divided by 6.02 times 10 to the power of 23. So I just took a moment to redo that calculation. I'm getting 0.052 moles, and some of your teachers may want you to convert that to scientific notation, which would give us 5.2 times 10 to the power of negative 2 moles, and that's of CO2. So hopefully you did okay with that calculation. That pretty much covers the gamut of it. I'd like to try one more question with you trying it on your own to see how you do, and then hopefully you'll do okay, and we'll take it up. So in this example, it says how many moles of magnesium phosphate can be made from a certain number of atoms of oxygen. And so to help you out a little bit with this question, I'm actually going to give you the formula for magnesium phosphate. And so magnesium phosphate has the formula Mg3 bracket PO4 bracket 2. Right? Okay, so give this question a try and then see how you do. The nomenclature and the formula here makes things a little bit more complicated, but hopefully you'll be able to navigate it. And then resume when you're ready. Okay, so in this problem, I'm going to start with what I know, and what's given to me is that 8.3 times 10 to the power of 23 oxygen atoms. And so my first step is going to be to get rid of that. I don't want oxygen atoms, right? I want formula units of Mg3PO4, formula units or particles, whatever. And so when I look at this whole thing, I can see that in 1 formula unit, there are 4 times 2 or 8 oxygen atoms. So by doing this, I'm basically dividing by 8 and grouping my oxygen atoms into particles of magnesium phosphate. And so now I'm not quite done, because all I've figured out now are how many particles of magnesium phosphate I have, which is not what I want. And so I need to keep going. And I'm going to say, well, all right, I want to get rid of my formula units of magnesium phosphate. And I want moles of that substance instead. And so I know 1 mole is going to have 6.02 times 10 to the power of 23 formula units of that magnesium phosphate. And I'm running out of real estate here, people. And so I work out that calculation, and I get 0.17 moles, and that's of magnesium phosphate. Okay, So hopefully you found this to be okay. Again, this will require you to have some prior knowledge of nomenclature and counting atoms and so on and so forth, as well as dimensional analysis. There will be some practice in class as well, but reach out with any questions you might have.